Okay, so we're going to talk now about carbon in the ocean. This is a figure from the IPCC, quite an old one now, but you can see on this that you have some carbon in the atmosphere, okay, but we have much, much more. So we have, I guess this may be up towards almost 700 now gigatons of carbon in the atmosphere. Ocean has got, even just in the surface layer of the ocean, there's more carbon dissolved in the whole of the atmosphere. And then in the deep ocean, there's orders of magnitude more. It's like 37,000, 40,000 gigatons of carbon dissolved in the ocean. Okay? And the reason for that, which we went over in the introductory video, is that when carbon dioxide dissolves in water, okay, so that's this guy at the top here, carbon dioxide goes from a gaseous phase into an aqueous phase. So that is determined, the relative concentrations of these two chemical species in the atmosphere and the ocean, that's determined by Henry's law. But as soon as you dissolve and form this aqueous CO2, it reacts with water. Okay, so these are not part of the Henry's law kind of relationship. So these are basically hidden away extra carbon that we can store in the ocean. Okay, and critically, the relative proportions of the key species, so this guy here, carbonic acid, doesn't really hang around much in the ocean. That's very unstable. So you can kind of add together the concentration of carbonic acid and the concentration of aqueous CO2, and that's almost identical to the concentration of CO2. So we kind of ignore it. But if we just take the total, so this is total dissolved inorganic carbon. So this is the sum of all of the carbon species. So it's a little bit counterintuitive that this symbol for this is sigma CO2, because it's not just CO2, it's the concentration of CO2 aqueous plus bicarbonate ion and carbonate ion. And it turns out that most of the carbon in the ocean is in this form, and the relative proportions of these is dependent on the pH of the ocean, so how acid it is. But critically, only the CO2 aqueous exchanges with the atmosphere. Okay, and that's kind of like just a reminder of what pH is. So pH is kind of the negative log of the concentration of hydrogen ions. That's not actually the true definition of pH, but that will do for now. Okay, and the ocean is slightly basic, so it's got a pH of about 8.1, 8.2. Okay. So because only this CO2 can exchange with the atmosphere, if we can change the relative proportions of CO2 aqueous to bicarbonate to carbonate, that means that we can change what the atmospheric CO2 concentration is. So because there's so much more carbon in the ocean than there is in the atmosphere, if the ocean really determines what the atmospheric concentration is. So if we start to acidify the ocean and make that there's proportionally more CO2 than there is this guy, that means that there'll be much more CO2 aqueous that can exchange with the atmosphere. So the CO2 concentration in the atmosphere will go up. Okay? And that's kind of summarized on this diagram here, which is basically showing the relative proportions of the different carbon species at different pHs. Okay? And critically, only the CO2 star here just means it's CO2 plus bicarbonate, but it could just be CO2. So at high pHs, so alkaline conditions, we have mostly carbonate ion, and that means there's not much CO2 to exchange with the atmosphere, so that means we can store loads of carbon in the ocean, because only a tiny amount of it can exchange with the atmosphere. Whereas if we suddenly then acidify the ocean, then all of that carbon that was locked away can exchange with the atmosphere. And we're super bad times. Okay, so just those dissolved forms of carbon, because you can switch between one form and the other, that to a certain extent can buffer these proposed changes in pH. So if you did something to the ocean, if you added some acids to the ocean, okay, what would happen is that, so I've just written out those equilibrium equations as kind of a continuous chain of equations at the top here. So if we added acids to the ocean, what would happen is that it would basically start to drive the equilibria towards the left-hand side, because we're adding in stuff that's on the right-hand side. Okay? So that means that if we try to acidify the ocean just by adding hydrogen ions, we change the relative proportions of the CO2 species, and that would counteract the change in pH. Okay? So just with the dissolved species, there is a buffering of pH change. But the ocean is not just dissolved forms of carbon, there are also inorganic solid forms of carbon. So these are calcium carbonates and calcium phosphate at the top. We'll kind of ignore the calcium phosphate at the top, but just think about calcium carbonate and what that does. So I've added these kind of reactions in the bottom, and I don't think you have these reactions in your handouts, but you should know them. So write them down. So basically, these reactions at the bottom, so this is precipitation. So this is us forming shells out of calcium carbonate. So we start out with some dissolved calcium and some dissolved carbonate in the ocean, and we grow a coral, or we form a bivalve shell. And that takes calcium ions and carbonate ions and forms calcium carbonate. Okay. The counter to that is if we maybe reduce the rate of calcification in the ocean, or we start to dissolve away organisms that have calcium carbonate shells. So if we start to dissolve away the Great Barrier Reef, we take our calcium carbonate that our corals are made of, and we dissolve them, and that returns calcium and, in this case, bicarbonate ions to the ocean. But it doesn't really matter what form of, whether it's carbonate ion or bicarbonate, we're adding to the ocean stuff that's on the right-hand side of these equations at the top. Okay? Or taking out. So if we have a think about what that means in terms of the CO2 system, and this is kind of really, really counterintuitive. So if we start to, let's say we start to grow a coral reef, okay, and that coral reef is made of calcium carbonate. So we're taking stuff that's got carbon in it out of the ocean, okay? But we're also removing carbonate ion from the ocean, okay? And if we have a look at what that does to this equation at the top here, okay, if we take this out, that's going to start to force the reactions towards the right-hand side, okay? And the effect of that will be to add hydrogen ions to the ocean, okay? So actually, taking calcium carbonate out of the ocean by growing coral reefs, for instance, that actually acidifies the ocean. So in the video, it talks about adding CO2 to the atmosphere, that acidifies the ocean. But you can also acidify the ocean by growing coral reefs, okay, which is odd. So if we wanted to counteract ocean acidification, we could dissolve coral reefs. And that would, we're adding this guy, which would force these reactions towards CO2, okay, which would remove the hydrogen ions, which would raise the pH, and that would actually mean that we're moving these equilibria more over to the right-hand side, and we're therefore lowering atmospheric CO2, lowering ocean acidification. It's quite counterintuitive. But it's all kind of explained on this diagram here, in that if you just think about what happens to the ocean pH when you add or remove calcium carbonate to the ocean. Okay, so if you think about calcium carbonate, if you have some HCl, some acid, and some calcium carbonate, the calcium carbonate is like it's an alkali, so it neutralizes the acid. So if you take it out of the ocean, you're reducing the amount of, if you take it out of the ocean by forming a shell out of it, which sinks to the bottom of the sea, if you're removing that acid neutralization capacity, that means you're making the ocean more acid. Okay, which means you move this way, which means that you're basically having more carbonate, more bicarbonate, and less CO2 as part of your total dissolved inorganic carbon, which means that you would then I've got that the wrong way around. See, that's how complicated it is, right? So you've got, if you start to precipitate calcium carbonate, you are removing from the ocean the neutralization capacity of the ocean. So you're making it less alkaline, you're making it more acidic this way towards having more CO2. So if you remove calcium carbonate from the ocean, it makes it more acidic, it makes it, the relative proportions of CO2, bicarbonate and carbonate, you get more CO2. Now you've removed carbon from the ocean, so the overall amount of dissolved inorganic carbon, so if you added up the CO2, the bicarbonate, carbonate, that would still be less, but the effect of being less matters less than changing the relative proportions of CO2, bicarbonate and carbonate. Okay, so to just think about that a little bit more in terms of what is this neutralizing capacity of the ocean. So there's this term called alkalinity, which is up here. So the alkalinity is basically a chemical term for the capacity of stuff dissolved in water to neutralize the addition of acid. Okay, and this arises because of a charge imbalance. So if you've got basically three pie charts here. So this is the composition of conservative elements in the ocean. I say so the things that don't really change in concentration. Okay, now that's in terms of mass. If you work out how many moles of these things, you get a pie chart that looks a little bit like that. But if you then normalise that to the charge on each of those ions, you get a pie chart that looks like this, where we've got the negative ones on this side and the positive ions on this side. Okay? And it looks like they kind of balance out, which is what you expect, because when you put your hand in the ocean, you don't get an electric shock. Okay? The ocean is electrically neutral. But if we look at this in a little bit more detail, so now I've just put these in two kind of bar charts. So these are the negatively charged anions on the left, positively charged cations on the right. And we have a close look at just this top layer. If you do, I think I got the concentrations of these off Wikipedia, so it must be right. If you add up the concentrations of all these things, you find that there is an imbalance. There is not enough negative charge in the ocean to counteract the positive charge of just the conservative ions. Okay? So that means there must be something else, this alkalinity we call, that basically makes up the rest of this negative charge. So a way of thinking about this is that we basically can define this difference in charge in the ocean as if we add up all of the charges of the conservative elements that are positively charged and take away the concentrations of the ions that are negatively charged. That gives us this total charge imbalance. So another way of working that out is basically what is actually making up that difference in charge. So then we look at some of the non-conservative charged species in the ocean. And those are these. So these are these things we've been talking about already. So bicarbonate, carbonate ions. See, this one counts twice because it's got a charge of -2. You have the borate ion here. So you have some OH ions, some hydrogen ions. All these other, some of the nutrients are charged. Okay. So if we add all up the positive, if we add up all the negative ones and take away all the positive ones, that gives us that charge imbalance there. Okay. Now the key thing is that so quite a lot of these have an exchange reaction between two different, or maybe even three different species that are dissolved in the ocean that allow them to change their total amount of charge. Okay, so if you look at the borate ion here, we can change the amount, the relative proportions of borate to boric acid. So this is boric acid here. This is borate, and that can balance any addition or subtraction of hydrogen ions. Okay, and critically for the carbon species, so these make up most of total alkalinity. Okay, so these are the most important ones. So that if we have, if we start to add hydrogen ions to the ocean, if we add negative charge, then we add positive charge, then we can basically counteract that by using up some of our alkalinity and forming one of these. Okay, so let's just take a step back and think about what's the actual effect of this detailed chemistry. Okay? So if we think about what happens if we add CO2 to the ocean. Okay? So this could either be by adding it from the atmosphere by burning fossil fuels, or in situ in the ocean by respiring organic matter. So we're adding carbon dioxide So that means that the total inorganic carbon, okay, the total concentration of dissolved carbon here must go up. Okay? But when we add carbon dioxide, and I'll use the pointer for those that hopefully will be watching on the video, if we add carbon dioxide, we are then adding hydrogen ions, because when carbon dioxide reacts with water, it forms hydrogen ions. So that means that the pH, okay, will go down, okay, becoming more acidic. Now, in this case, it won't have any impact on alkalinity, because we're adding to the ocean ultimately bicarbonate ions and carbonate ions, but we're also adding an equal amount of hydrogen ions. Okay, so adding CO2 to the ocean acidifies the ocean, but doesn't affect its capacity to neutralize that acid. Okay? Now, if we think about dissolution of calcium carbonate, okay, so we get some coral reef, we start dissolving it. So we're adding, in this case, maybe carbonate ions, okay? So we're going to increase the amount of carbon in the ocean dissolved because we're adding one of the components of DIC, dissolved inorganic carbon. Okay, but when we do that, we are also adding alkalinity to the ocean. Okay, because we're adding one of the components of this guy. Okay, and we're actually removing a hydrogen ion if that carbonate reacts with a hydrogen ion to form bicarbonate. Okay, so this means that the pH will go up and alkalinity will go up. So if we dissolve CO2, if we dissolve calcium carbonate, we are increasing the total amount of dissolved organic carbon, but we're also moving that speciation. We're moving the relative proportions towards having more bicarbonates. We're moving over to this side of things because we're making the pH higher. Okay, so this means that by dissolving the calcium carbonate, there's actually going to be less of this CO2 present because we're moving more to the right-hand side of this diagram, which means that if you dissolve calcium carbonate, there will be less CO2 to exchange with the atmosphere. Okay, so dissolving coral reefs will reduce atmospheric CO2. Okay, so this is kind of a summary of those changes. So on the left-hand side, this is production of organic matter, okay, which is kind of the opposite of the respiration, which we've just mentioned. So if we produce organic matter, then we're removing dissolved inorganic carbonate, but the pH will go up, alkalinity won't change, and we're reducing the atmospheric CO2 because we're drawing down organic carbon. But if we form calcium carbonate shells, which is the opposite of dissolving the Great Barrier Reef, we remove dissolved inorganic carbon, but we acidify the water, okay? Which means that the atmospheric CO2 will ultimately go up. And this is a problem. I guess I said this is the Great Barrier Reef, so this is kind of one of the areas I do some research. This is a cruise I went on, we mapped it and dredged it, which was kind of bad. So dissolving this would be great for the atmosphere. Not so good for tourism or biodiversity. Okay, so if we look at what are the impacts of what we've just discussed about the different effects of producing organic matter or producing calcium carbonate on the carbon cycle. So this is kind of, we add nutrients to the surface ocean, there's some sunlight, and life happens. Okay, that will produce plankton. They'll have some organic matter in it, but it will also produce plankton that have got calcium carbonate shells. So this is coccolith here. You also might grow some coral reefs. So you're removing you're forming organic carbon, but you're also forming inorganic carbon. You're also forming calcium carbonate in the surface ocean. That means that the efficiency of these things, which we talked about the other time, so this is basically the carbon pumps. So this is organic carbon. So we form organic carbon in the surface ocean that removes CO2 and that exports it into the deep ocean. That would lower atmospheric CO2. But if the same plankton have got calcium carbonate shells, we remove that calcium carbonate in the surface ocean. So we're removing alkalinity, we're lowering the pH, which means we'll actually increase the atmospheric CO2. Okay? So if you want to sequester carbon dioxide in the ocean for geoengineering reasons, or you want to explain your paleoclimate records, then it's really important that you know something about the ratio of organic matter production to carbonate production, to calcium carbonate production. Because if you have the same amount of those two, it won't change atmospheric CO2 at all. Okay, so the type of plankton you get is really important. Okay, and again, this is because if we precipitate calcium carbonate, it moves our pH to lower values, which means that although there's less total carbon in the ocean, there is more CO2 to exchange with the atmosphere. Okay, so this is just to summarize that effect on this biological carbon pump. So this is the pumping of carbon dioxide into the deep ocean so it's not in the atmosphere. It's really dependent on this thing that's sometimes referred to the PIC to POC ratio. So that's the particulate inorganic carbon, so calcium carbonate, to the particulate organic carbon. So if you produce lots of this, you draw down CO2. If you produce lots of this, you don't. Okay, so just quite briefly, so we talked about these two kind of carbon pumps, the organic carbon pump, the inorganic carbon pump, and how they kind of counteract each other in an annoying way. But there's also, I want to think about this effect of temperature. Okay, so we know that CO2 is much more soluble. You get much more CO2 into cold water than warm water. Okay, and that explains some of the surface patterns we saw. But also, if we look back in time, in colder periods, so this is many thousands of years in the past. These are glacial, interglacial cycles. So this is the last glacial maximum. So the blue is a proxy for temperature. Not put the scale on because I'm slack. But when it's colder, there was less CO2 in the atmosphere. So this is kind of a slightly circular argument in that we know that low CO2 in the atmosphere will lead to a lower greenhouse gas effect. Okay, more CO2 makes it warmer, but also it works the other way around as well. So if you make the planet colder, that leads to more CO2 being dissolved in the ocean. Okay, so the colder it gets, the more CO2 we can put in the ocean. So this is kind of one of the climate feedbacks that can amplify natural variation in the Earth's kind of like climate, okay, by changing the temperature of the ocean, which can determine how much CO2 is in the atmosphere, and therefore the magnitude of the greenhouse gas effect. Okay, so again, this is another summary which will be available on the thing there. So important things are the temperature and the efficiency of these biological pumps, inorganic and organic, and also the ventilation of the deep ocean. So if the oceans circulate very slowly, okay, that gives the water more time to accumulate carbon from the surface ocean, okay, more time to lose oxygen. So if you circulate the oceans more vigorously, you can store less extra carbon in the deep ocean, and more of it will be in the atmosphere. So ocean circulation also has a strong control on the distribution of gases between the ocean and the atmosphere. Right, we're almost at an end here, so I just thought I'd show this up and just to give some evidence for this ocean acidification effect. Some of you might have done this in ELE, in my practical, but you can see here the red curve is atmospheric CO2 going up, and then the blue curve is a measure of the dissolved CO2 in the water, okay, in Station Aloha, which is just off the coast of Hawaii. You can see that closely follows the rise in CO2, and that's driven by this Henry's law relationship. If the atmospheric CO2 goes up, the ocean CO2 should go up as well. And you can see here the impact of that in terms of the ocean pH, that as the CO2 is going up, we're acidifying the ocean. Okay, pH is going down. And just finally, I thought an example from the geological record would be quite neat. So this is kind of longer term change. So this is now 0 million years, and this is 65 million years ago here. So the dinosaurs died here. And what we're going to do is we're going to look at this event here. So this is the Paleocene-Eocene thermal maximum. sometimes called the late Paleocene thermal maximum. But you can see this is this green curve is a proxy using oxygen isotopes that's thought to relate to global temperature. Okay, so you can see there's a big spike in global temperature just here, and this is that record, but flipped on its side. So we've got 55 million years ago to 54 and a bit million years ago, and instead of oxygen isotopes, now we're looking at carbon isotopes on the left. And this is a kind of a proxy for stuff happening in the carbon cycle, either adding carbon that's got a different isotopic fingerprint, or changing the cycling of carbon in the ocean. But you can see that there was a big perturbation in the carbon cycle here, and it turns out that this was thought to be the addition of either an enormous amount of methane or CO2 into the atmosphere. Okay, so this is a big global warming event, and that explains that spike in temperature. But if we look at what's happened to the sedimentary record here, so this is that same sedimentary core here, you can see it's kind of light coloured and then suddenly goes dark coloured because all of the calcium carbonate has started to dissolve. Okay, and that's what we see on this right hand side here. So at different depths in the ocean, we can see that the calcium carbonate is being dissolved away. And that's as a response to this increase in CO2 and this ocean acidification. Okay, so the take-home message I want you to get from this slide is that if you dump loads and loads of CO2 into the atmosphere, and this is kind of analogous to what we're doing now, right? We're just totally screwing it up, right? What will happen is the ocean will acidify, which it's doing now, and that will cause the carbonate in the ocean to dissolve. And that dissolved calcium carbonate in the ocean, that will raise the alkalinity, it will increase the buffering capacity of the ocean, which will eventually reduce the atmospheric CO2 concentration by changing the speciation between CO2, bicarbonate, and carbonate. Now, the important thing I want you to remember is that this process took from here to here, so that's 100,000 years. Okay, so that's the kind of time scale that we're looking at. The ocean will repair what we're doing to the planet, but it will take at least 100,000 years, which is kind of too long to wait, really. Anyway, bit of a downer, but anyway, so this summary, which I think you have. Do you have this summary? I was nice and gave you the summary. So this is stuff that kind of you should know. That should be subscripted. That was an error. Okay, so that's me done for today. Tomorrow, it's not me. Sorry about that. I have to go somewhere and do some stuff. So I think you have Simon tomorrow, and then I'll switcheroo back in later on. Yeah, so if you've got questions about life in general or oceanography, post them on the discussion forum, and I'll attempt to address them. I'll do a demonstration about some of the CO2 stuff in the practical on Tuesday for those that are coming to that. Alrighty then.